Hello everyone, so today we're going to go over section 5.4, mutually exclusive events. So what are mutually exclusive events? In any experiment, if the events A and B have no common outcomes, then they are called mutually exclusive. So an example of this would be if you roll a die and then you have odd numbers as event A, or even numbers as event A really, that works too, and then odd numbers as event B, then what you will notice is that it is impossible for events A and B to both occur at the same time, so they are mutually exclusive. Let's say instead events A and B are, let's say event A is the outcomes 1, 2, and 3, and event B is still the odd numbers, then they are not mutually exclusive because they have shared outcomes, in this case 1 and 3. So they're not mutually exclusive. Okay? So if they have no common outcomes, then they are mutually exclusive. If they have a common outcome, they are not mutually exclusive. Some quick examples here to see if we fully understand the idea. A dice roll, so basically the example that we already have above. These are mutually exclusive events because it is impossible to roll a number that's odd and even at the same time. Okay, so next up we have drawing a card from a deck of cards. A face card is selected as event A, and event B is heart is selected. So again, we want to consider if it's possible to have common outcomes, and in this case there are, and they are the Jack, Queen, and King of Hearts. So these two events are not mutually exclusive. So next up we have two dice thrown, probability of both dice showing the same value, so doubles, and then event B is the total is 11, so total of course is the sums. So if they have same value, so you can have 1 1, 2 2, 3 3, 4 4, of course, and then 5 5, oops, 5 5, and 6 6. Alright, the total is 11. There's only two ways to accomplish that. We either have a 5 and a 6, or a 6 and a 5. And you'll notice that there's no common outcomes in events A and B. So of course these are now mutually exclusive. Okay, so one more. We have four different events. F is if the card is a face card, we draw a random card out of the standard deck of 52. K is if the card is a king. S for spades, and H for hearts. So what you notice is that the only two events that are mutually exclusive are S and H. Because you cannot draw a card that is a spade and a heart at the same time. However, for any of the other two, you can always find a common outcome. Example of this would be you can find a face card that's a king, you can find a king that's a spade, you can find a king that's a heart, and of course you get face cards that are spades or hearts. So really, the only two mutually exclusive events are spade and heart at the same time. So one way to write out outcomes is using a diagram such as the one we have here. So we are using dots to represent favorable outcomes. Each dot is an outcome here then. And there are 13 dots in total. 4 of them are belonging to event A. So the probability of event A is 4 out of 13. The probability of event B, as you can see, is 3 out of 13. A couple of new symbols here. You can see the one that looks kind of like a U. This is the union symbol, which mathematically basically means or. And the one that's upside down from the union symbol, that's the intersection symbol, and that means and. So if you look at what it says probability of A or B. So anything belonging to A, and there are 4 outcomes belonging to A, or belonging to B, and there are 3 outcomes belonging to B, will count as probability of A or B. So that's really 7 out of 13. And for the intersection, well, you can see that A and B, they do not intersect. So there's 0 outcomes that they have in common, which means the probability is here 0. And the important thing to kind of draw back to what we have been talking about is that A and B are then mutually exclusive. If their intersection is empty and that probability is 0, then the events are mutually exclusive. Okay, so moving on. Here, what is the relationship between the probabilities of A, B, and P, A, or B? So in this last example, because the events are mutually exclusive, we can actually just add the probabilities together. 4 out of 13 for the probability of A, 3 out of 13 for the probability of B, and they add up to 7 out of 13 for the probability A or B. So that basically means that we have the equation probability of A plus probability of B is equal to the probability of A or B. Now this only works if A and B are mutually exclusive. Oops. Okay, let's look at a second diagram. You can see in this case A and B, they share a common element. So the math will be slightly different here, and we probably have to come up with some more generalized equations for this one. So the probability of A will be 1, 2, 3, 4, 4 out of 13, because you have to count the one that's in the middle. Probability of B, of course, will be 5 out of 13, just the same way of finding that out. Probability A or B counts everything that's inside of both circles, so that will be 8 out of 13. And the intersection has exactly 1 outcome in it, so that's 1 out of 13. So you can see that we cannot just use the same formula as before because it doesn't add up quite correctly, right? 4 plus 5 is equal to 9, not 8. And the reason for that is because you will count the common element twice. So what we have to do is adjust the formula slightly to generalize it for both not mutually exclusive events and also mutually exclusive events. So this would be probability of A plus probability of B minus the probability of A and B, and that would be equal to the probability of A or B. Okay, and that's kind of the key for today because it applies for mutually exclusive events and also events that are not mutually exclusive. If the events were mutually exclusive, this number here will simply be 0. This number right here. Okay, so talks briefly about intersecting and disjoint set. So if the part where they have a common element is not empty, then they're intersecting. Otherwise, they're disjoint. And again, the formula is given to you right there. So we're going to use it for a couple of questions here. It says Jane and Victor are playing a board game. To move on this turn, Jane must either roll doubles or sum of 7 of 2 standard dice. Let's see. So doubles will be these 6 outcomes. So the probability of doubles, of course, is just 6 out of 36, which of course is 1 over 6. 1 over 6, sorry. Sum of 7, 6 plus 1 is 7, 5 plus 2 is 7, 4 plus 3, 3 plus 4, 2 plus 5, and 1 plus 6. So those are the different ways you can get 7s. So that's 6 out of 36 outcomes as well. Now, if you were to apply the formula, then the probability of doubles or 7s would just be the sum of the two. And that's because these two events are mutually exclusive. You cannot roll 7 and have doubles. It doesn't work. So this would be 1 over 6 plus 1 over 6, which is 2 over 6, which is 1/3. All right. Similar question for part example number 5. Different rule. Sum of that's greater than 8 or a multiple of 5, they get a bonus 100 points. So let's look at the outcomes that are favorable there. Multiple of 5 would be 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4. And the other multiple of 5, of course, is 6 plus 4, 5 plus 5, and 4 plus 6. So that will be 7 out of 36 outcomes that are multiples of 5. So we're going to write it 5x 5 times. So that's 7 out of 36. All right, and then the other one is greater than 8. So that will be all the outcomes that are 9, 10, 11, and 12. And there are 10 outcomes that are greater than 8. Greater than 8, 10 out of 36. You notice that in this case, there is actually an intersection. The intersection of the two groups will be anything that's a 10. So the probability of 5 multiples and greater than 8 is 3 out of 36. And the question asks the probability that Victor will receive a bonus 100 points. So that is the same as calculating the probability of either multiples of 5 or greater than 8. So that will be 5x or greater than 8. And as we saw, the probability formula is probability 5 multiples plus the probability of greater than 8 minus the probability of the intersection. Oops. And of course, that would be 7 over 36 plus 10 over 36 minus 3 over 36. So that would be 14 over 36, which is the same as 7 over 18. Okay, so next part is just about cards and how we can use the mutually exclusive events, or if they're not mutually exclusive, then how do we subtract the intersection? Face card over club. Sorry, we're finding the probability of getting face card over club if we draw a card randomly from a standard deck of cards. So there are 12 face cards out of 52. There are 13 clubs out of 52. And there are 3 cards that are club faces. So the Jack of Clubs, the Queen of Clubs, and the King of Clubs. So if you do some adding and subtracting here, you'll get 22 out of 52, which of course is the same as 11 over 26. 8 or spade. So there are 4 eights. Let's do it in a different color. 4 eights out of 52. There are 13 spades out of 52. There are 1 8 of spades. So if you add those together, you'll get 16 out of 52, which you can divide. You get 4 out of 13. Okay, next up is looking at the probability of drawing a black card or a diamond. So this one's slightly different. There are 26 black cards in the deck of cards. There are 13 diamonds. These two events are actually mutually exclusive, so you simply add together the probability. You will get 39 out of 52, which is 3/4, which makes sense because you're essentially trying to draw any card that is not a heart, and 3/4 of the deck will be not a heart. And the last one, just really quickly, we are looking at there are 4 jacks out of 52. There are 26 red cards out of 52. And there are 2 red jacks, a jack of hearts and a jack of diamonds. So if you add those together, you'll get 28 out of 52, which is 7 over 13. Okay, so some quick examples here using a deck of cards. Last one requires you to draw a Venn diagram to help sort it out. So let's try to do that. We will start with a box, and then inside we'll draw 2 circles. Because this is if you read the question, is a Venn diagram involving 2 groups. Okay, something like this would suffice. All right, so it says here we have people who have smartphones and people who have tablets and people who have both. So if you read the question over, there are 30 people with both smartphones and a tablet. So that's done. There are 80 people with smartphones. This includes the people with both a smartphone and a tablet. So really, the people with only a smartphone will be 80 minus the 30 in the middle, which means 50 people have smartphone only. Likewise, on the other side, this would be 40 minus 30, which means 10 people have just a tablet. Now, since 100 people are surveyed and the number of people inside the 2 circles add up to 90, there are 10 people who are left out. So for us, then once this Venn diagram is solved, the probability of a person has a smartphone or a tablet, this would be the probability of S or T, and that would be 9 out of 10. And the probability that a person has neither of those will be 1 out of 10. So we looked at how to use Venn diagrams. We talked about what are mutually exclusive events and what are not mutually exclusive events, and the probabilities involving each one of those scenarios. And that's it for today. Thank you for listening.